Hello everyone. So this is going to be the lecture, week 3 for angular kinematics of human movement. In this lecture, we're just going to go over some of the rules of angular kinematics, or our units, some of the math for it, and then why we look at angular kinetics. But once again, as I said, when we were talking about linear kinematics, most of the mathematics for angular kinematics is shared with linear kinematics. So when we look at angular displacement, angular velocity, angular acceleration, we'll look at the equations for that, but we'll see that they're very, very, very much the same when we're looking at linear kinematics as well. So we need to understand this because most human movement involves rotation of one or more segments about a joint to cause motion. So our muscles pull on our bones and our bones rotate around a specific joint. So once again, if we're looking at kind of the full picture, is our limbs are moving within a plane. Let's say we're doing lower leg extension. Our quadricep muscles are going over our knee joint and pulling up on the lower leg, or at our shin, or tibia, or the tibial plateau, and that leg is moving within the sagittal plane, but around the mediolateral axis, which would be our knee joint, okay? And we need to be able to understand, well, how fast is that leg moving? How much did it move? How much rotation is occurring at that knee joint? And a lot of times when we're looking at this stuff, we use motion capture. Motion capture, we simply have, it's usually, at least in our lab, we have 2 labs, one with 10 cameras, the other one with, I believe, 12 cameras. And they're very, very fast capture cameras. They actually track these little reflective markers, use a different color, these little reflective markers right here. And we oftentimes draw angles, which we can see in this picture right here. We can see this picture, and it's simply is used to calculate kind of our angular kinematics, angular kinematic values. And then we can use these values to do many things. We can use them to create avatars. If we wanted to create avatars for stuff like this, for video games, for CGI movies, everything like that. But in our lab, we don't really do that, but we're looking at how is this person moving to help answer our questions. If we're looking at fall prevention, we could say, well, how quickly does their center of mass leave their base of support? Do we see dysfunction at one of these joints that leads to that center of mass? So a lot of times we use kind of a quantitative analysis, and we're looking at the angular kinematics of human movement. So once again, what I said is we use the qual-assist motion capture, and we track the position of certain anatomical landmarks to understand the angular kinematics, especially with angular components. So we've already kind of seen this video, but what we'll do is we'll put tracker markers on this woman here and have her do her motion, and then we will get a video, something like this. Now we'll look at this video a lot, but what we're really using these cameras for is to collect raw data, and we simply then use that raw data to calculate our specific values. And then we usually use those values to do some fun statistics to calculate whether they're being different, whether the angular kinematics are sufficient to perform a motion, can they be improved, and so on and so forth. Once again, we use that. This can be used to make video games. Madden, the football video game Madden, uses motion capture to track the motions in football, and then they simply overlay an avatar of an existing player onto those values, and we see realistic motion. This is done with humans. There's video games where they have animals. A lot of times, a motion capture company that I've worked with in the past, one of their side parts besides clinical stuff, they work with video game companies, and they do a lot of dogs, horses, and like that, where they'll put little markers on horses, have them trot around just to make sure that if we're playing video games like, I don't know, like Red Dead Redemption, that horse is moving in more of a realistic way, so we're not to break immersion of the video game. And once again, we do this in our Veer Lab. This is kind of the big thing we do in Veer Lab. If any of you have ever been to this lab before, usually in this class, we bring you into the lab and show you this stuff, and we'll put markers on you, show you how to do stuff. But sadly, due to kind of the campus shutting down for COVID-19, we're not going to be doing this. But once again, if you're interested, please feel free to contact us, either the grad students or the professors in kinesiology, and say that you're interested in this stuff. We would be more than happy to have you guys come in. You can work as a research assistant if you just want a tour of the lab and how to do stuff. We are more than happy to meet with you and take you through the lab and help you understand stuff more better. So can't do it this semester, but hopefully in the fall or following spring, if you're interested, you can come take a look at our lab. So when we're looking at angular kinematics, we have to make a distinction between a relative or absolute angles. A relative angle is an angle of one segment relative to another. So in this picture here, we are looking at the angle of our trunk to our thighs, okay? And we use this for our hip angles, our knee angles, elbow angles, ankle angles, shoulder ankles. This is where we're kind of looking at segment analysis of angular kinematics. We're determining the angle between one segment and another segment. And that's where we look at, a lot of times, if you've heard of the term range of motion, we're really looking at relative angles. And our angle, the origin of our angle, is always at a joint. Then we have absolute angles, which are angles formed between a segment of the body and a horizontal or vertical frame of reference. So we can look here, we can look at the thigh angle or trunk angle, but here we can look at the ankle between our thigh and, let's just say, this imaginary horizontal plane right here. And we can say, well, you know, if we're looking at picking up a box, we have this almost 90-degree angle. We would more or less, if we wanted to be very specific, we'd be looking at an angle of the hips to our horizontal plane. This is one of our things we look at. You know, you shouldn't lift with your back, especially when you're picking up something heavy. You should be lifting with your legs, because we're placing a lot of, we haven't kind of gone over it yet. We'll talk about it when we start looking at kinetics. But by doing this, we're increasing this lever arm right here, and we're placing torque, which is a rotational force, okay, on the lower back. And that's where we see a lot of our back injuries, is we're placing all this force on the lower back and spine. And this is where we start seeing muscles getting injured. Most lower back injuries are actually muscle pain. We can see, you know, damage to the actual vertebrae and spinal cord as well, and the nerves associated with it. But by far, a lot of kind of our lower back pain is just due to poor biomechanics. People lifting up boxes poorly, poor posture while sitting in a chair, and everything like that. So a lot of times when we look at this, you know, we try to not do a whole lot of surgery to fix lower back pain. So that's where we look at, you know, the role of a physical therapist, not only in relieving back pain, but hopefully teaching the correct motions and they understand biomechanics well enough that they can teach correct motions as a measure of secondary prevention. So when people, if they're, you know, a FedEx loader, they'll learn the correct way to move those boxes so we don't see recurring back pain. Okay, so when we make these measurements, they're always with a segment and our horizontal or vertical frame of reference. And the tools we use you can use a protractor. You can place a protractor on this figure here, And if you remember how to use a protractor, you'd put the straight line here and measure this angle from that line. A lot of sports medicine people, sports medicine personnel, physical therapists, we use a goniometer, which it looks just kind of like a compass. And you have two arms here, and then it's 360 degrees marked out right in here. This arm is fixed, so you'd put this against the horizontal plane, and this arm moves back and forth, and it'll kind of indicate that absolute angle. And then once again, we use motion capture systems as well. So to understand kind of all of angular kinematics, we need to define and you need to understand what the center of rotation is. The center rotation provides knowledge of the underlying joint anatomy and is essential for proper location of a joint center. To really understand and find the correct place to put a marker for motion capture, your goniometer, you need to kind of understand anatomy well enough that you could locate where the center of the hip joint is, or where the center of the knee joint or shoulder joint is. Because during motion, the bones form a joint, and this is where we see that actual resultant rotation occur. So let's look at our angular kinematic values or quantities. Remember, these are essentially the angular components are very similar to our linear components. So we have angular distance and displacement. But instead of saying for our linear, we'll write these out. So this will be 1, 2, 3, 1, 2, 3. For angular distance and displacement, we're using degrees instead of meters, okay, or kilometers or centimeters. For this class, once again, we're using meters. But as you progress through your career, you'll see other linear measurements. We'll use degrees. We may use radians or revolutions, and we'll look at those later. For angular speed, we're still keeping our seconds. Time is still always measured in seconds, but we're just using our degrees instead of, once again, our meters. Okay, so the only real difference is we're simply changing units. Instead of meters, we're looking at degrees or radians or revolutions, and angular distance displacement, just the degree. Angular velocity is degrees per second. Angular acceleration is degrees per second, or degrees per second squared. So we can express, once again, our angular kinematics in kind of three different ways. We can talk about revolutions. For speed, we're looking at revolutions per second, or velocity, we're looking at revolutions per second, degrees per second, or radians per second. It's kind of a helpful conversion unit to know that 1 radian is 57.3 degrees. We use radians instead of degrees a lot of times, or we'll convert degrees to radians if we are trying to convert rotational motion to linear motion. Because once again, if we're looking at a lot of biomechanics, we're looking at humans and we're trying to determine, well, how much linear motion is produced by that rotational motion in the lower body for gait. And it's kind of helpful to know that 1 radian is 57.3 degrees. You can usually figure this out if you do kind of the pi conversion, pi r squared conversion. But if you don't want to do that math, you can simply remember that 1 radian is 57.3 degrees. So we can just look at some other ones. Basically, half a revolution makes a 90-degree angle, and that would be pi divided by 2. Okay. Same thing with half a revolution is 180 degrees. We can see this right here. So that's 180. That's 90. That would be pi rads. And remember, pi is simply 3.14. For all the really cool people that can go beyond 3.14, I can go up to 10. I'm not that smart, but I'm a nerd. So we like counting to pi as far as we can go. And then we have 3/4 of a revolution. We have 270 degrees, and that's equal to 3 halves of pi radians. And then finally, one full circle, one full revolution is obviously 360 degrees, and that's 2 pi. So let's look at angular distance and displacement. Remember, with linear distance and displacement, with linear distance, we are following an entire path, okay? This is our distance. But for displacement, we're just looking at a straight line from point 1 to point 2. It's not a perfect straight line, but you get the point. And remember that displacement is never greater than distance, okay? So angular distance is measured during the path, along the path of rotation. And this is a scalar quantity. It doesn't have a direction. It just has a magnitude. And then angular displacement is the change in angle from the first to last position. This is our vector. So not only does it have a magnitude, it has a direction. We see in this picture here, we're starting here. This is a simple pendulum. Goes here, going back and forth like this, you know, and then eventually when it settles, it goes here. So we measure this displacement. This would be our displacement from first to final. We can have many different displacements from 1 to 2, 2 to 3, but these are all separate displacements. So this right here would be our angular distance, but this is the distance between these points is our angular displacement. So let's look at some examples. And remember, displacement is simply the difference between point 2 and point 1. In angular kinematics, we're looking at the distance, the angular displacement, between angle 2 and angle 1. So we have this batter right here, and he's swinging from 150 degrees to 210 degrees, the angle of his bat with, we'll say, this imaginary vertical plane. So we simply take the difference of angles. We have 210 minus 150 gives us an angular displacement of 60. Then we have somebody performing dorsiflexion, okay? The angle between their foot and lower leg, so this angle right here, you do a different color, you can see it better, okay? That was making an angle of 100 degrees. But they then did dorsiflexion, and then we had an angle of 130 degrees. So now we're taking 130 minus 100, so we have an angular displacement of 30 degrees. And then finally we have, we'll just say we have this imaginary plane again. This would be our imaginary plane. And we have an initial angle of 160 degrees, so this person right here. And then they begin, we'll say this was a high diver. They leaped off the ground and their trunk was making a 160 degree angle with our imaginary horizontal plane right here, okay? And then they begin to tilt downwards and their angle increases to the ground to 210 degrees. So we take our 160 and then minus that 210 degrees, so we have a negative 50 degree displacement. So when we start looking at kind of our other kinematics, we have angular speed. This is angular distance over time. The same thing with linear speed, just put it like that, is equal to linear distance over a change in time. Angular velocity, this is omega, but think curly W equals omega. But this is the change in angular displacement over time. So kind of our linear component to this is linear velocity is equal to linear displacement over a change in time. And then we have angular acceleration, which is alpha. And this is simply a change in angular velocity, which is omega, over a change in time. And so this would be degrees per second squared, or you'll see it written out like this, degrees degrees per, degrees per second to the -2 is the same thing as this. But our kind of linear acceleration, once again, was a change in linear velocity, usually measured in meters, over a change in time, okay? So it's not really, and we'd see, it'd be meters per second squared, okay? So once again, these are the angular components of motion, or angular kinematics, and they're very, very similar to our linear kinematics as far as how we calculate them. So our angular velocity, once again, this is a change in angular displacement over time. So let's look at those 3 examples again, but let's add time as a component so we can calculate our angular velocity. So we have 150 to 210. So we take 210 minus 150, and we'd have, I think it's 60 degrees. We then divide by 0.62 seconds. So they swung the bat from 210 degrees to 150 degrees in 0.62 seconds. So their average angular velocity was 96.8 degrees per second. We can do the same thing when we were looking at dorsiflexion. We went to 130 to 100 degrees. So once again, we take 130 minus 100 and divide by time. They did this in 0.45 seconds. And so we have 66.7 degrees per second. Remember your order of operation. So first you do your addition, subtraction stuff, then you do your division. And then our last example, they had a absolute angle of 210 degrees, and they transformed to 160 degrees. So we take 160 degrees minus 210, then we divide by 1.4 seconds. So we take 50. So 160 minus 210 is 50 degrees, divided by 1.4 seconds, and we have negative, because I should have said this was negative, excuse me. Oop. That was negative 50 degrees. Okay, so if we subtract, or if we divide a negative number by a positive number, we have unequal signs, we'll have a negative value here. So they performed this movement with an average velocity of 35.7 degrees per, or negative 35.7 degrees per second. Now, how can you tell if something is rotating, or if angular motion is positive or negative? Generally, we consider counterclockwise rotation to be positive and clockwise rotation to be negative. There is no real great reason for saying this. We just kind of, when our species started doing physics, we just kind of all agreed that counterclockwise rotation is positive, clockwise rotation is negative. And we like to say that too, is if we look at, the rotation of planets, especially our own planet, our planet rotates in a counterclockwise rotation. Okay, so we'll say, well, then, that's positive rotation. Another good way is to take your right hand and kind of point your fingers in the direction of the rotation. So we see this first one here, okay? He's pointing his fingers in the direction of this rotation. He's curling his fingers around it. If your right thumb is pointing upwards, that's going to be positive rotation. If you have to grab it where your thumb is pointing downwards, that's going to be negative acceleration. I hope that makes sense. Because when we look, especially when we look at displacement, which leads to our velocities and accelerations, we need to determine if that's going to be a positive or negative velocity or acceleration. So let's look at a couple examples here. During a kick in soccer with the right leg, are our velocities positive or negative at our hip, knee, and ankle? So if we're looking at our hip, if we're kicking, we're going to be doing, whoops, moving like this, okay? So that is our counterclockwise rotation, so we're going to have positive velocities. What about our knee? Our knee is moving forward like this. I'll use a different color for that. Get rid of this. We'll use red for this one. Our knee and basically our lower leg is going to be rotating like this. Okay. Once again, that's counterclockwise rotation, so it's going to be positive. Now, obviously, the leg doesn't do a full rotation, but you know the rotation is counterclockwise. And then finally, our ankle. We're going to be doing dorsiflexion. So the foot, get a different color again. The foot is going to rotate again in a counterclockwise rotation. So our dorsiflexion is also going to have a positive rotation. Plantar flexion would be the opposite. Plantar flexion, the foot's moving like this. Use a different color, sorry. Moving like this. That's clockwise rotation. So we are going to see negative velocities. Okay? So does flexion and extension indicate the sign? No. The direction of movement indicates the sign. So if we see hip flexion and knee extension, we're both positive. But if we're looking at hip extension, where I'm going to get rid of some of the stuff to clear it up a bit. But if we're looking at hip extension, okay, hip extension is going to move like this. That's our clockwise rotation, okay? This would be negative. If we're looking at knee flexion, get rid of some of this stuff. If we're looking at knee flexion, where the lower leg is going to rotate around our ankle like this, that's clockwise rotation, so it would be negative. So it depends on how it's rotating, not whether it's flexion or extension. So let's talk about our angular speed and velocity. Moving segments at a higher angular velocity is usually a characteristic of skilled performance in many sports. Pitchers, we see that, you know, most, like our professional pitchers, they will rotate their arm approximately 6,180 degrees per second, or 17.17 revolutions per second of internal rotation in the shoulder. And then we see almost 5,000 degrees per second at the elbow of elbow extension. These are peak velocities. They're not average velocities. So by the end of that pitch, if we're looking at kind of our summation of forces and our kinetic link principle, this is what we see at the very end of that pitch. This is why, too, when you look at these values and then start adding in the masses of arms, lower arms, hands, and even the baseball, you can see, especially major league pitchers, and if you've taken anatomy, you know about the rotator cuff muscles. And in pitching, we see a lot of pitchers usually have torn rotator cuff muscles. A lot of times, this is the supraspinatus rotator cuff muscle. This is the one that sits right under the, believe it's, oh, I forgot. It's not the acromioclavicular. Yeah, it is the acromioclavicular joint. Believe so. And that joint, when they're doing overhead motion, we see a little bit of deformation of that joint. So I'll just kind of draw it right here. This is our AC joint, not an artist. We see almost depression on that on our supraspinatus muscle. This is a lot of times where we start seeing the damage to the rotator cuff muscles when they're doing that very forceful overhead rotation. And then our elbow, we start seeing, especially if they're doing curveball pitches, this is where we start seeing a lot of tensile force to the kind of medial collateral ligament of our elbow joint, right here, we'll say this is our humerus, this is our forearm, and we're seeing this medial force right here. This leads to kind of tearing of that ligament of the elbow. This is where we start looking at pitchers getting Tommy John surgery, where they take out the torn medial collateral ligament of the elbow and they'll put in a tendon to replace that. And that's where we start seeing, that's what a Tommy John surgery is. Okay, so let's take a look at how pitchers throw a ball. So this is Drew Storm of the Washington Nationals. And we'll start seeing he's going to pitch in slow motion here. This is where we start seeing that kinetic chain of forces and our summation of forces. And this is where we start seeing the rotation. Right about here is where we start seeing that force on the shoulder joint, then force at the elbow joint, and then finally the release of the ball. So kind of the summation of our angular forces and angular rotation lead to the linear velocity of that ball. This is where we're looking at rotational or angular kinematics being transformed into linear motion and linear kinematics. A few other things to look at. If we're looking at figure skaters, the difference between a triple axle versus a single axle. In this, a body is a projectile. To increase rotation, we have to either increase the time in the air or the angular velocity. I hope that makes sense. What we're saying is if they want to complete 3 rotations versus just 1, while they're in the air, they either have to spin faster or stay in the air longer. Usually what professional skaters will do is they will use their legs and hips to produce enough torque before they leap into the air so that they will be able to perform a greater angular velocity. So they can perform a triple or quadruple axle. And then, they'll do some other things. They'll tuck their arms into their side. This reduces the moment arm of their body. We haven't really talked about that yet. We'll talk about when we get to kinetics. But by reducing that moment arm, they're reducing the torque needed for that rotation. So they're basically they're kind of almost storing energy, and that will accelerate them if you do that. Good way to test this out if you're sitting in an office chair that allows you to it spins, is start spinning in your office chair and then tuck your arms and legs towards you, and you'll start going faster. If you then throw them out in front of you, you'll start slowing down. Simply that, we're changing the length of our moment arm. So skaters will increase angular velocity to complete triple or quadruple axles, which may be up to 5 revolutions per second or 1,800 degrees per second. So let's look at angular acceleration. Much like linear acceleration, for it to occur, there needs to be a force. Remember, things don't change direction, things don't change their movement characteristics just because. A force is responsible for that. We remember that linear acceleration, I need my pen back, linear acceleration is equal to linear velocity, the second linear velocity minus the first linear velocity divided by a change in time, and that's our meters per second. With angular acceleration, we're looking at the final angular velocity minus the initial angular velocity divided by time. Okay, so we're going to have degrees per second squared, radians per second squared, per second squared. We may have revolutions per second squared. Okay, so once again, it's not really, as far as calculating stuff, it's not any different than our linear kinematics. So if we had a rotation of 100 degrees per second, but then increased our linear velocity to 180 degrees per second in roughly a half a second, we simply take our final angular velocity or our second angular velocity and subtract our initial angular velocity and divide that by time, and we get 80 degrees per second squared. Okay? I'm sorry, 160 degrees per second squared. So, with linear acceleration, remember that linear acceleration, can either be positive, negative, or zero. Okay? Usually we say that if it's positive, we see a positive net force. We're seeing velocity increase. Negative means the velocity decreased. Zero means velocity stayed the same. So in angular acceleration, a positive angular acceleration can mean that either angular velocity increased in the positive direction or decreased in the negative direction. So once again, our positive direction is our counterclockwise motion, and our negative direction is clockwise rotation. Okay? And then if we have negative acceleration, that means that either the angular velocity decreased in the positive direction, it slowed down, or it increased in the negative direction, means it sped up going in a clockwise rotation. So once again, clockwise, counterclockwise. Okay? I hope that makes sense. If not, you can kind of go over this a few more times. So what is the difference between linear velocity and angular velocity? Usually we can look at this with this equation right here and see that we can actually convert linear velocity to angular velocity and angular velocity to linear velocity, but we need to know the radius of rotation, this right here. This is a lot of times is where we start converting our degrees to radians. But let's look at a quick example. Okay? A person is swinging a bat at a maximum of 1,588 degrees per second. What is the linear velocity of a baseball after the bat contacts that ball? We need to get from degrees per second to meters per second. So from an angular to linear components, where v is the linear velocity, omega is the angular velocity, and r is the radius of the baseball bat swing. Usually, it's very important that you have to convert angular velocity from degrees per second to radians per second. Okay? So let's take a look at how we'd... Okay, so let's look at this equation and try to solve it. So we know that the bat's angular velocity was 1,588 degrees per second, and we do know that when we're swinging a baseball bat, we are swinging it in a counterclockwise motion. Okay, so we'll say counterclockwise motion. So it's going to be positive. Okay. And when we're going to assume that this is a right-handed batter. If they're a left-handed batter, it would have been clockwise motion. But forget about that for right now. But we'll say this is counterclockwise motion, so it's positive. They're swinging their bat at 1,588 degrees per second. And we know that we can then calculate the velocity of the ball is equal to the angular velocity times the radius of the bat. The bat is 1.1 meters. Okay, so we simply first convert our degrees to radians. There's 57.3 radians, or 57.3 degrees per radian. So now we have 27.7 radians per second. And so we multiplied that 27.7 radians per second by 1.1 meters, and we get that if the bat contacted the ball, that ball would then travel at 30.5 meters per second. Okay? Hope that makes sense. All right, so let's see if it's important, if the calculation of linear velocity from angular velocity, let's see if the radius of rotation is important? Well, if we first simply look at our equation here, v equals angular velocity, or linear velocity equals angular velocity times the radius of rotation, we can see it's a multiplication problem. So the radius of rotation is just as important as angular velocity. And depending on our magnitudes, it may be more important. But let's consider two different cases. We're going to still say that the bat is rotating at 27.7 radians per second, but the ball is hit at different points on the bat. One, it's hit at 0.8 meters up the bat. The other, that it's hit 0.5 meters up the bat. So let's try to solve this and see if that makes sense. So for our first example here, we still have v equals omega times the radius of rotation. So v is going to be equal to 27.7 radians per second times 0.8 meters. That's going to give us, get my calculator out because I can't do that stuff in my head. That's going to give us 22.16 meters per second, but we're only reporting to our three significant figures, so that's going to give us 22.2 meters per second. Let's look at the other case. With instead of 0.8 meters being the radius of rotation, we have a half a meter. So we still have v equals omega times r. So we're going to have v equals 22.7 times 0.5 radians per second times meters. That will give us basically half of 22.7, so 11.35, I think. But just to double check, I'll redo it on my calculator. So 11.35. Okay, so we're going to have, due to 11 having a leading 1, we still have three significant figures, so 11.35 meters per second. So generally, the larger the radius of rotation, the faster we're going to see our linear velocity. Okay? This is kind of another good way to look at this is if you're riding a bicycle that has different gears. Generally, if you want the pedals to be easier to push, you'd go down to a lower gear, and the radius of those gears is smaller than the higher gears. Those have a larger radius, okay? So it makes it easier to push your pedals. But you'd have to push your pedals at such a rate, at such an angular velocity, to maintain the same speed. You can turn your pedals with a larger gear. I hope that makes sense. So let's continue. Let's expand kind of the relationship between linear and angular motion. Remember this equation, okay? Granted, it will be given to you on any sort of exam or homework, but knowing these equations so you don't have to look them up just kind of speeds up the process. So let's look at another relationship here, okay? A bat is swung from point A to point B in approximately 1 second, okay? For point A, the bat has an angle of 50 degrees and a radius of 0.3 meters. So its angular velocity is going to be either 50 degrees per second, or if we convert it to radians, remember that there are 57.3 degrees per 1 radian, it would give us 0.87 radians per second. If we then multiply that by 0.3 meters, we have, if it hit a ball, we'd have, that ball would travel at 0.262 meters per second. For B, we still have an angle of 50 degrees, but a radius of 0.7 meters. So we're going to have an angular velocity of 50 degrees per second, and our radius, if we convert it to radians, that's going to give us still 0.87 seconds. But if we multiply this by the greater radius, 0.7, we're going to have a greater linear velocity of that ball, 0.611 meters per second. So the length of the radius of rotation, or the magnitude of the radius of rotation, is just as important as angular velocity when trying to convert to linear velocity. So in baseball, you need to achieve a higher angular velocity of the bat and impart a higher linear velocity to the ball, okay? So it's been estimated that a difference of 1 millisecond, so that's 0.001 seconds, in a swing or in swing initiation can send the ball to the center field versus the foul line. So a swing of 3 milliseconds too early or too late would result in no contact with the ball. It would either go to the right or left foul poles. So if we're looking, we haven't talked about kinetics yet, but a good way to look at this is if we want to really hit the ball far, we would need to swing the bat quicker, correct? If we need to swing the bat quicker, we need a greater force. Now, this kind of gets into, especially if we're looking at baseball, is it's harder to swing a bat harder, and it's harder to initiate the swing. It's harder to direct the bat if you're swinging it harder. So you might, if you hit the ball, it will go further, but you might miss it all completely. So a lot of times when somebody is having difficulties contacting the ball, a lot of times what they'll do is they'll choke up on the bat. You know, they'll, instead of holding it at the end of the handle, they'll hold the bat further up. What that does is it makes the bat easier to swing. So they're able to direct the bat better and hit and have a greater chance of hitting the ball. But when they do that, it's harder for them to hit the ball further. So a lot of, especially in baseball, a lot of batters will not necessarily be known to be home run hitters, but they're just as important because they are known that they can at least get the ball in play and put runners on bases. Runners on bases are just as important as a home run because they represent significant points. Okay, so sometimes you want to hit the ball, sometimes you just want to get it in play. Okay, so note that both the radius, the length of the bat, and angular velocity contribute to linear velocity. Therefore, if a bat has a greater radius, meaning it's longer, but it's too heavy for the person to swing quickly, they don't gain anything. When we look at Little League players, they use lighter bats. In college players, they use aluminum bats, which are lighter than wooden bats. I personally think that college players are developed enough they should be using wooden bats, but that's so they can hit the ball harder, okay? So is the takeoff linear velocity of the ball the same as the linear velocity of the bat at contact point? No. Ball velocity is also influenced by how the ball is hit and the elasticity of impact, okay? So if you hit the ball square with the bat, it will contribute much more elastic energy and kinetic energy, so the ball will travel further versus you just hitting the top or bottom of that ball, which would lead to either a ground out or a foul ball or something like that. So that is the end of the lecture. I hope this was helpful. And then once again, if you still have questions about angular kinematics, please feel free to contact me. I'm more than happy to help you. Goodbye.